Okay, let's start. So, a very good evening to everyone. This is live problem solving session number 10 for course entitled Basic Thermodynamics, Classical and Statistical Approaches. And this course has course code NOC24CY04. And myself, Akash Gutal, I am a PhD student from Indian Institute of Technology, Jodhpur, Department of Chemistry. So today, before going towards the solving the problem, uh, we will cover certain things, certain formulas that covered last week. And this, I think last week we have only uh, covered one topic, which is uh, which is thermodynamic free energy, and all four lectures, all another four lectures was the tutorial problems. I think you have done that tutorial problems while doing your lectures. So in the last lecture, that is thermodynamics free energy. So we will discuss certain formulas related to the same first, and then uh, we move towards the today's problems. So this will be a revision for the last week. So what we have seen in the thermodynamic free energy lecture is uh, the first equation is about differential about the internal energy, which is internal energy is the function of S, V, and N. So we have introduced the concept of chemical potential in this bit. And if you write it in differential form, which is TdS minus PdV plus mu dN, where we know that T is equal to change in internal energy divided by partial change in entropy, constant volume and number. Mu is change in internal energy divided by change in uh, number at constant entropy in volume. The third quantity is minus P is equal to change in internal energy on change in volume at constant entropy and number. So minus the P also we have seen um, in previous lectures that it is a internal pressure. Okay, del U by del. And we defined what is the equation of state. I will write the definition. The equation of state is differential, or we can say equation of state is derivative of the fundamental equation. So in thermodynamics, you have equation of state, and it is the derivative form of the fundamental equation. So fundamental equation is the equation which gives entire information about the only that equation will give entire information about your classical thermodynamic or the thermodynamic system. And the equation of state is nothing but the it's a derivative form of the fundamental equation. Also, the equation of state, uh, we have seen in the lectures that it kills the information inside the fundamental equation. Means it is not the entire form. The entire system is actually expressed properly by the fundamental equation. And if you use the multi-component system, for multi-component system, we have seen for multi-component system, we defined the change in internal energy, the change in number of that ith component at constant entropy and volume is nothing but mu I. So this way we have defined the chemical potential species I. Okay. Similarly, we have derived from the equation second law of thermodynamics, del S plus first law, and using first and second law of thermodynamics, we have derived uh, del H by del S as at constant pressure is temperature, and del H by del P constant S or entropy is volume. And most importantly, we have derived partial change in entropy divided by partial change in temperature. Constant volume is Cv by T. And similarly, the change in entropy, partial change in entropy divided by partial change in temperature at constant pressure is Cp by. Okay, these two equations we have seen at the end of the lecture. So these are the some revision of the formulas that are needed to solve problems. So we will move towards uh, the questions part. Okay. So here is question number one. The partition function for a two-level system, the lower state at energy zero being non-degenerate and the upper state at energy epsilon being doubly degenerate is given by. Okay, simple question. Take 2-3 minutes of time. Solve it on your paper, and if possible, tell me the answer. Do the calculation. Take your own time. It's simple. You need to calculate the partition function. You must know the definition of the partition function, and using that, you can easily calculate. We have discussed in last discussion session that if the level has a degeneracy, so how we incorporate in the equation of partition function, we had seen in the last week's discussion session. So use that same formula and try to calculate the partition function for this particular problem. So this problem, we have a two-level system. The lower state energy is zero, being non-degenerate, and the upper state is epsilon, energy with energy epsilon, and it is doubly degenerate. Means there are two. So there are two degenerate level for the upper state. So, so the formula for partition function is, so let's say the capital, we have used capital Q. Q is equal to summation of e raised to minus epsilon I by kbt. Right? So use, and in this equation, the degeneracy occurs. We need to put at each for degeneracy for each energy level multiplied by 3 raised to minus e by kbt, epsilon by kbt. So what we will get is q is equal to, so the degeneracy of downshift is 1, will be e raised to minus 0 divided by kbt plus the degeneracy of upper state is 2 by e raised to minus, its energy is epsilon kbt. So that this value will be 1, and your partition function will be 1 plus 2 into e raised to minus epsilon naught epsilon upon k. This is your partition function, and it is option number C. Sorry, option number D. Then the next question. Uh, this question we will solve at the end. It had some problem. So question number 3. Which of the following quantity represents entropy? So there are four options are given. Let me know the which is the correct option. Take your own time. Take 2 minutes. Just 2 minute job. Take care of sign. Take care in this question. The sign minus KB is given. Check whether it is true or not. So it is K here in this equation. Consider as KB. Okay, KB. It should be KB. Okay. Same. The Boltzmann's constant. So we will solve this question. The KB is KBLNW, the first form. We know the entropy. This is famous Boltzmann's equation. LNW. W here is the number of microstates. So this is Boltzmann entropy. Boltzmann entropy equation. Second form is S is equal to minus KB summation of I PI into PI. This here the PI is the uh, probability. Okay? PI is the probability, and we have seen this equation last lectures, last week's lectures, and this form is this summation of PI ln PI, or if you can say it's a negative summation of PI ln PI. This form we have seen it is Shannon entropy in information theory. And the physical entropy we can find uh, using multiplying it by the Boltzmann constant. Okay, and this form of entropy that we have seen is called the Shannon entropy in information theory. So the significance of negative here, it's also called negative entropy. It doesn't mean that the entropy is negative, but it means that because it is entropy, because it related to the P, that is the your probability factor. Probability always is less than one. Because of that, the logarithm value will come out as negative always, and this outside negatives cancel out, and this value always stays positive. So the entropy is always stays positive. Because of that factor, the negative is included in this equation. So that's why it's also called the negative entropy. And the third equation is the standard definition of entropy as change in heat of the system, reversible, the change in heat of the system during reversible process at given temperature T is also the definition of entropy. And hence, all of the above statements are represents entropy. The next question. In an experiment where a coin is flipped 4 times, we note the following four distributions with probabilities pH and PT as 0, 1, 1 by 4, 3 by 4, 1 by 2, 1 by 2. Which distribution has the highest number of microstates? The four options are given. Try to calculate. Take your own time, 2 3 minutes. The hint for this question is you can use the same Shannon entropy to determine um, the highest number of microstates. So in this problem, we have the coin is flipped for 4 times, okay? And we note the following four distributions with probabilities are given. And four, it's not four, it's given is three, okay? And which distribution has the highest number of microstates? So how we determine this is we know that natural logarithm of microstate is they were very closely equal to summation of probability of ith component into natural log of probability of ith component. Fine. So same way we can calculate the number of microstates, the natural log of the microstates for each system. So let's calculate ln for this first 0 1 system. It's nothing but summation 0 ln 0 plus 1 ln 1. Okay, this will be 0 minus 1 ln 1, which gives you, we calculate it. It's just ln 1 uh, and 0 if you the same thing, which is nothing but minus ln natural log of 1. And for second system, 1 by 4, 3 by 4, which is, and we know that natural log of 1 is 0 which is nothing but we can put directly 0. And the second system is can write as 1 by 4, which is, let's write in decimal form, 0.25, and then 0.25 plus 3 by 4 is 0.75, and then 0.75. And if you calculate it, minus of 0.25 minus of 0.25 natural log of 0.25 plus 0.75 into natural log of 0.75, which gives you 0.5656233. And for third system is 1 by 2 and 1 by 2. The minus 2 into 1 by 2 is 0.55 into ln 0.5. If we calculate it, 2 into 0.5 cross natural log of zero point 0.5 will give you 0.6931. This is the highest. So this is the highest value for 1 by 2, 1 by 2. Option number 3. In a different way also you can solve. The number of microstates are maximum when you see all energy levels, or we can say all the outcomes are equally probable. So and using that definition also, uh, the option C is right. Half probability is equal probability for the both uh, outcomes. Because of that, the highest number of microstates will be for the system in the option number 3. So next question. For a three-level system, following Maxwell-Boltzmann distribution in the following table, find the average inertia. Okay, try to calculate this particular problem. We need to calculate average inertia. Take your own time, 3 to 4 minutes. First, calculate the partition function and then calculate average energy. So we know by the definition of uh, partition function, Q is equal to summation of Gi e raised to minus epsilon I by kBT. So put the information on the equation. The first level is having energy 0 with the degeneracy 2 plus second level have degeneracy 2 to e raised to, and the energy is 2 kBT, plus the third level has degeneracy 1 with energy is 4 kBT. And this will reduce us to 2 plus kBT kBT get cancel, 2 cross e raised to minus 2 plus e raised to minus 4. So that will give you, if you calculate, 2 plus 2 cross e raised to minus 2, which is 2 plus e raised to minus 4, which gives you partition function 2.2889. You approximate it, then it will come out to be 2.29. Okay. And we know the average energy, how we calculate is so we can say it's energy of the ith system into its degeneracy into its uh, e raised to power term with its energy divided by kBT. And if we do summation overall divided by the partition, okay. So what we'll get, we have the first energy level is 0. Uh, uh, First energy level have energy 0, has energy 0, and so it will be 0 plus the second is 2 kBT into 2 into e raised to minus 2 plus 4 kBT into 1 into e raised to minus 4 divided by 2.29. You solve this, Let's take KBT constant. I will be having 2 cross 2 into e raised to minus 2 plus 4 cross e raised to minus 4, which will give you 2 cross 2 e raised to 2 minus 2 plus 4 cross e raised to minus 4, which gives you to calculate it will be 0.2695 kb. Average energy is, and it turned out to be 0.27 kb. And the answer is option number A, or the first option. Fine. The next problem. So the problem, question number 6. Consider a lattice with n sides and n green particles. Consider another lattice adjacent to the first with m sides and m red particles. Assume that n plus m sides are available to all the green and red particles. What is the total number of configurations available? The 4 options are given. Please calculate this problem carefully. Take your own time, 3 to 4 minutes. Calculate it. So it's a sort of derivation, and we need to use the same background, the same way we have calculated the number of microstates for the system. Same formula, that n factorial divided by n1 into n1 factorial into n2 factorial into n3 factorial. The same way you need to calculate. But here there are lattice sites uh, which are vacant. Some lattice sites uh, in the green, for the green particles, and some lattice sites in case of m or the red particles are vacant, and you need to take care of that vacant sites also in your derivation, uh, in the in calculation of the number of microstates. Remember, this lattice sites also indistinguishable. And the green particles are themselves must be indistinguishable, and m red particles also themselves will be indistinguishable. So, but uh, m and n are different. So, same way, we need to consider the same thing. But the lattice for both the system are common. Common in the sense they are having same form, and they can also be considered as indistinguishable. So we have n sides. So there are, let's say, n sides, and suppose there are green particles, and some sides are vacant. Okay. There are similarly we have red m sides, and they are also filled with red particles. And when we join this, so assume that n plus m sides are available to all green and red particles. If we combine the both, so if we combine the both, then n plus m sides will be available for both the particles. But there are G indistinguishable particles, and there are R or the red indistinguishable. Sorry, there are N green indistinguishable particles, and there are M red indistinguishable particles. So we have total number of sites are n plus m, and so we need to find out what are the number of microstates. So we know, suppose we have n number of uh, sites, then the same formula we know that n factorial divided by n1 factorial, n2 factorial, n3 factorial is n1 and n1, n2, n3 are types of particles. Okay. So in this case, we have n plus m number of sites, take factorial of it, divided by for the first uh, for first kind of particles, that is green particles, this will be n factorial. For red uh, particles, m factorial, because they are indistinguishable. This the bottom terms, the n factorial, m factorial are because coming because they are indistinguishable. So we need to uh, divide by the combinations uh, or the number of permutations of these similar distinguishable particles. So this will neglect out from total number of microstates the combinations that are or the permutations that are forming because of the indistinguishable particles. So and third thing is we can consider this vacancy because it is indistinguishable. We can consider it as like a particle, but indistinguishable particle. So that number of sites will be the total number of sites n plus m minus the sites occupied by n green particles minus the sites occupied by m red particles and the factorial of that. That will give you the total number of microstates. Fine. So your answer should be option number A. So the basic thing in this is the the, these two sites are also indistinguishable. If you change them, they it doesn't matter. So they are indistinguishable. They can be considered as one of the entity that determines the macrostate. So given a two-state system in which the low energy level is 800 calorie per mole, and the higher energy level is 1200 calorie per mole, the temperature of the system is 400 Kelvin. The partition function we know, formula for partition function is summation of Gi e raised to minus epsilon I by kBt I2. So can calculate it. The degeneracy is 1 for both the system, both the energy level, and e raised to minus the first energy is 800 kilocal per mole divided by kBt, or we for kBt, if we convert it into um, kilo calorie per mole, that turn out to be 1.987 into the temperature is 400 plus e raised to minus 1200 divided by 1.987, 400. We calculate it and get the answer. E raised to e raised to power minus 800 divided by 1.987 into 400 plus e raised to minus 1200 divided by 1.987, 400 0.5864. Your answer should be option number second. Fine. So the next question. What is the probability that exactly one of the top two cards of a standard well shuffled deck of cards is a heart? Four options are given. Please try to calculate. Take your own time. Take 3 to 4 minutes. So the probability you need to calculate. So there is a well shuffled deck of cards, and you need to take out two top two cards, uh, and we need to calculate exact probability of one of that card is hurt. Even you take any two cards and with well shuffled deck, I mean you need to choose two cards from that well shuffled deck. The problem is saying the same thing, and but the condition is that the exactly one of that two card, uh, exactly one card should be the hurt. First, we calculate to take out the number of ways we can take out two cards from the well shuffled deck of cards of number 52. So that would be combination of two cards from the 52 cards. Just simply simple combination. That would be 52 factorial divided by 50 factorial into 2 factorial. That will give you 52 cross 51 cross 50 factorial divided by 50 factorial cross 2 factorial, and that will give you 226 cross 51. Okay, which so what is the number? 26 cross 51 is calculate 26 cross 51 1326. So 1326 number of ways you can take out two cards. Then we will see what is the probability from that two cards, uh, that one is hurt and another is any other any other card, but it should not be the heart itself. So that probability, so in 52 cards we have 13 hearts, so will be this will be any heart from the 13. Okay, and and other cards are nothing but the remaining one, which is 39. So total number of combinations are nothing but the 13C1 cross 13C, 39C1. So that will give you 13 cross 39. And that number is, so 5078. 507 number of combinations can occur where of the two cards from the 52 number of 52 cards, where one of the card is hard. So we need to just need to calculate the probability, and the probability is number of possible ways of getting a two card with exactly one card having hard, and divided by total number of possibilities, 1326. If you do it, you get 0507 divided by 1326 is 0.3824, and that answer is option number A. Okay. So the next question. So there are 8 chocolates uh, and 6 vanilla ice cream balls. Two balls are selected one by one without replacement. Find out the probability that the first is vanilla and second is chocolate. 4 options are given. Please try to calculate. Take your own time, 3 to 4 minutes. So there are 8 chocolates and 6 vanilla ice cream balls. Two balls are selected one by one without replacement. So if you have the total number of entities are 8 plus 6, which number for a number of 14. Two balls are selected one by one without replacement. The total number of ways selecting this into using this fashion is 14C1 cross 13 because it's without replacement 13C1 that will give you 14 cross 13 which nothing but to calculate is 14 cross 13 is 182 and the probability that the first is vanilla and second is chocolate. So first is vanilla and second is chocolate. So vanilla, uh, which we will get as first, the probability will be so we'll be having 6C1 and this will be uh, 8C1 chocolate having probability 8C1 across. Total number of their own combinations will be 6 cross 8, which is 48. And the probability you can calculate of possibilities divided by total number of entire possibilities. 48 by 1. And the answer is should be option number C. And so that's ends the today's problems. If you see, we have left one problem. Uh, this one. So this problem, I think it's a little. I found some absurdity in this problem. I will discuss in the next session if possible. So we have half an hour left. If you have any problem, because this is the 10th week, I think next 2 week only we have the sessions. If you have any problem regarding any question which in the which have completed in the past discussions, you can ask. I will be here till 9 p.m. So you can ask. So thank you very much for attending the session. We will meet next week, Tuesday, 7 to 9 p.m.